So here we go into transformation of functions. And I want you to know transformations we will talk about for every single parent function that we discuss this year. And so this is a very important video, and the next one that you understand completely. The next thing I want to remind you is the definition of a function. A definition of a function is that for every input value, there's only one unique output. So, is this a function? Yes, this guy is definitely a function. So, I'm going to use this for this video. I know it doesn't look like anything that you've ever graphed before, but we're going to use this for the purpose of a visual. The other thing I want to make sure you understand is that all functions have a parent. So when you were learning lines last year, you learned that the parent of a function, the parent of the linear function, is y equals x. Really, in Algebra 2, we're going to refer to it more as f of x equals x. You learned that the parent of the quadratic is y equals x squared. Again, we're going to refer to it as f of x equals x squared. Remember, to talk about this, we say that the function with x inputted is x squared. So if I input an x into here, I'm going to get the f of x. The ordered pair for that would look like this. X, my output would be f of x. That's the same as saying x, y. Okay, so this guy right here is going to be our parent for this entire video. Okay, the last thing I want to do is I just want to, because we just did inverses yesterday, I just want to show you that I can actually find the inverse of this function. So I really like doing the inverse using a table. So I have the point negative 4, 0. I have the point negative 2, 0. I have the point 0, 3. I have the point 1, negative 1. And I have the point 3, 1. If you remember, if I want to find the inverse using a table, I just flip those around. 0, negative 4, 0, negative 2, 3, 0, negative 1, 1, 1, 3. So 0, negative 4, 0, negative 2, 3, 0, negative 1, 1, and 1, 3. And if I were to connect them in order, notice I made my table from left to right, then I plotted them left to right, then I connected these left to right. So we talked about what it would look like graphically, and graphically it should look like that blue graph is reflected over the line y equals x, and you can see that that is the case. This particular point reflects here. This particular point reflects across here. This particular point reflects across here. So I found my inverse tabularly, but I also am going to double check it graphically. You know, in math, I have always hated it when all they show me are a bunch of letters, because math should be numbers. But I want to make sure you understand what the transformation general form looks like. Okay? In math, there are 4 transformations, and if you remember from geometry, transformations can be reflections, they can be translations, they can be dilations, they can be rotations in geometry. Typically, we don't rotate in algebra. So I'm just going to give you a quick overview. These two guys will end up being either reflections or dilations. These two guys are going to end up being translations. Okay, and I'm going to refer to A, B, C, D transformations all year. I'm going to give you an example that you probably have already seen. So if I were to give you this, that's a line, right? Well, you studied in Algebra 1 what that 2 does to a line and what that 7 does to a line. So I want to rewrite it in the form that you see above, just so you can see. Okay, so this is 2 times the parent function minus 7. So the parent function of this, we know, is the linear parent function, which is x, right? So this is saying 2 times the linear parent function, subtract 7. And you already know that that would give me a steeper line, and then that would shift me down 7. If my y-intercept in the parent function is 0, that obviously, if I start at -7, shifts me down 7. If my slope here is 1, this is going to double my slope, giving me a steeper line. I'm going to just put a word in your head and call that a stretch. We're going to stretch that line up really high. So this is the general transformation form. So again, the rest of this video would be talking about this particular parent function. This isn't a line, it isn't a quadratic, but it is a function. So we're going to refer to this function as f of x. So f of x is this function right here. Here's my table for that function, here is that graph. Now, like we started talking in the last one, what if I took f of x and I said, give me a new graph, g of x, which is going to be equal to f of x plus 3. So we already talked about what does this do in a line. If I add 3, that's going to shift me up 3. This is a D transformation all the way here at the end. I know that that already shifts me up 3. It changes the y-intercept on a line, yes, but what it does to a function is it shifts every point on the function up 3. So, what does that affect? That affects my y. This particular statement says g of x is going to be the original function plus 3. So here's my original function. What am I adding 3 to? Am I adding 3 to that number right here? Or am I adding 3 to g of x? I'm adding 3 to g of x. So if I add 3 here, I'm going to get 3, 3, 6, 2, 4. So I'm now going to plot those points. -4, 3, -2, 3, 0, 6, 1, 2, and 3, 4. And I'm going to connect them. It's going to be very important for you to keep your tables in good order. Notice my points, my x inputs are my inputs from left to right. I didn't do this input, then this input, then this input. They go left to right. So I plotted them left to right and connected them left to right. Therefore, when I now plot these new points for the new function, g of x, if I just connect them left to right, I'm going to get the same graph. So my new function is g. What did that D transformation do? Well, now you know that a D transformation does a vertical shift up or down, depending on what that D value is. So D transformation is a vertical shift up or down. And all I need to do the D transformation is, if this is plus 3, I'm going to add 3 to all of my y's. If this is a -7, I'm going to subtract 7 from all of my y's. The next thing I want to do really quickly is I want to look at the domain and the range of each of those. So we're going to look at the domain of the blue function first. We're going to look at the domain of this. Remember, domain, from your notes the other night, is left to right. What x values does this use left to right? So domain of the blue function, and notice if you aren't using color, you're going to need to write domain of, I guess you're going to write f of x, because that's my first, is left to right. So I use everything from, let me just put in a dotted line, here to here, every x between there and there, and I have a point here. So I'm going to use integral notation, and remember, if I have a point at -4, I put a hard box, and I have a point at +3. The range of the blue one, or f of x, is going to be bottom, here's the bottom point, to the top. And that is going to be -1 to +3, and I have points at both. Now let's talk about the domain and range of the red. So I have domain of the red, which is g of x, if you want to refer to it like that. I think from here on out using colors is going to be very helpful. The domain of the red one goes left to right. It didn't change at all. So the domain of the red one. What about the range of the red one? Well, the bottom is here and the top is here. So I went from 2 to 6. So my range went 2 to 6. I want you to see geometrically what that did. So remember geometry and translations. What did that do? Well, I took every point and I translated it up 3. Translating up 3 affects my y, but it doesn't affect my x. So notice my domain stayed the same. But what did I do to every y? I added 3 because of this. Let's look at one more example. So again, we have the same f of x. But what if I wanted my g of x to be 2 times my f of x? 2 times my f of x. Well, we know that in a line, if I did 2 times x, that would just give me a steeper slope. Okay? So, what does this do? What this is saying is I would like my output to be 2 times my original output. So I want to take f of x, the output of f of x, and multiply it by 2. So this is an A transformation. And I'm actually going to change that to a -2 so that we can see what this does. So all I do with a -2 is I multiply my y's by a -2. So if I multiply this by a -2, this is what I get. So let's see what happens. I plot the point -4, -2, sorry. -4, 0, -2, 0, 0, -6. One, 2, and 3, -2. And I'm now going to connect them. So what did it do? I want you to tell me what geometrical transformations happened to this particular guy. Growth mindset. Write down what you think. So the A transformation does two things. The A transformation reflects it across the x-axis. But notice it also did a stretch. And it is a vertical stretch because we're going to be looking at horizontal stretches tomorrow. It is a vertical stretch. So not only did I take this blue guy and reflect him across the x-axis, but notice this distance from the origin to the top point is 3. This distance from the origin to the top is 6. So I stretched him by a factor of 2. So lastly, let's look at the domain of the red and the domain of the blue. The domain of the blue isn't changing. It's my parent, and I've already written it on here. The domain of the red is going to be, again, left to right. So left to right, left to right. So my domain isn't changing. What about the range? The range is going to be bottom to top, bottom to top. Always start with your smallest number, so -6 to +2. So my range is going to be -6 to +2. Again, because of the effect that this has is only on my y variable, you notice that my domain doesn't change because my domain is my x variable, right? All my x inputs. My range has changed by the factor of -2. If I multiply this by -2, I get 2. This by -2, I get -6. The order switched because I want to go smallest to largest. You guys have a great night.